Today we have two vocabulary words, functions and relations. Functions and relations are both the same in that they're rules. It's a rule where you put one number in and you get something out. You put something in, you get something out. The things you put in, you call the domain. That's another vocabulary word. And the things that come out are called the range. Anything that comes out is in the range. The difference between functions and relations is that with functions, when you put something in, you're guaranteed to get only one possible thing back out. With relation, it's not like that. For instance, with a relation, you could have a rule that says, example of a relation, whenever I say 5, you say 2. Whenever I say 5, you say 3. Whenever I say 5, you say 7. So you're not really sure what it is you're going to say. You could say any one of those things whenever I say 5. A function's not like that. With a function, when I say 5, there's only one possible thing you can answer me with. That's the difference between a function and a relation. A function is like a machine. You drop something in, something comes back out. The things that you drop in have to come out of the domain, and the things that come out of the function, it's called the range. So an equation like this, y equals 3x plus 7. It's a linear equation. Y equals mx plus b. 3 is the slope, 7 is the y-intercept. This is a function because if I put in the number 2, 3 times 2 is 6 plus 7 is 13. The only thing you can tell me back is 13. You can't say 7 or 3. The answer has, that's the function. A function has a distinct answer for any input. The input's in the domain, the answer's in the range. Let's try to make this more clear. A function's a rule where I say a number and you say a number. So the number I say is in the domain. So I say 1, you say 4. I say 2, you say 6. I say 5, you say 10. So no matter what I say, for sure you know what you have to say. The independent variables, that's the domain. That's the stuff that I say. The dependent variables, that's the response. That's what you say back. Depending on what I say, when I say something, you have to say the right answer. So I'm independent. I could say whatever I want. Any one of these numbers I could pick. But you're not independent. You have to say the responding number. For functions, every question has exactly one answer. Here's another rule. It comes in XY pairs, coordinate pairs. If I say 1, you have to say 4. If I say 2, you have to say 6. It's another way of writing this exact relationship. Every element in the domain, exactly one answer comes out of the range. All right, let's look at another example. Okay, so now in this example, this is not a function. It's a relation, but it's not a function. So let's remember what the rule is for functions. Every domain, that's the things that I say, the things that go into the function, you get back only one element in the range. That's the stuff that you respond back with, the things that come out of the function. That's the range. Okay, so why is this relation, and this is a relation, why is this relation not a function? Well, when I say 1, you say 4. You know what to do. But what happens when I say 5? What do you say? You could say 6. You could say 10. That's not a function. It's okay for me to have choice of what I say, but you cannot have a choice of what to respond back with. This is not a function. All right, now another way of writing this exact same relation is with coordinate points, x, y coordinate points. X, y. x, y. It's the way you write coordinate points. This is exactly the same description of a relation as this is. When I say 1, you say 4. When I say 1, you say 4. But when I say 5, you could say 6, or when I say 5, you could say 10. You don't know what you're supposed to say back. That means it's not a function. A function is a relation. Function is a relation, but function is a relation in which you know what you say back. You know what comes out of the function machine. You drop a 5 in, you have to know what's going to come out. In this case, you don't. Could be a 6 pops out, could be a 10. That's not a function. Two different answers for 5. Notice also in this relation that when I say 2, you come back with a 6. And when I say 5, you also come back with a 6. Well, that's okay. It's okay for you to have the same answer for different questions. But it's not okay for you to have different answers to the same question, if you see what I mean. It's all right for 2 and 5 both to have the same answer, 6. But it's not all right for 5 and 5, the same question, to have two different answers. Let's look at another example of a function. This doesn't have an equation. It just tells you what to do. In this function, it's players on a basketball team. It tells you how tall that player is. So you measure each player. That's your function. However tall the player is, that's your answer. So the first player on the team is 6'2". The second player is 6'5". Notice that there's two different players that are both 6'4". That's okay. You measured the players. They are as tall as they are. What would not be okay is if player 2 was both 6'2" and 6'8". That wouldn't be okay because you don't know how tall player 2 is. It's got two different heights for the same player. Okay, let's look at this relation. Why is this relation not okay? Why is this not a function? Well, you know how tall player 1 is, 2, 3. You know how tall player 4 is. Player 5 doesn't have a height. That's not possible. If there is a player, he must have a height, or she must have a height. So it's not possible, but it's not a function, because every function, you have to know exactly what to do for every player. For every input from the domain, the players, you have to know what the answer is. What's the range? What is the height of that player? Well, for player 5, you don't know. So there's no answer for player 5, so it can't be a function because it doesn't tell you what to do for one of your inputs. Let's look at another example. Okay, this is not a function. What's wrong with it? Well, we have player 3, 4, and 5 are all 6'4". Is that a problem? Is there something unusual about that? No. It's a common height for basketball players. So you not only possible, it's expected. You have different people of the same height. There's not an issue there. So why is this not a function? Well, how tall is player 3? Is he 6'8" or is he 6'4"? You don't know. Okay, so that's not a function. There's your problem. Okay, let's go again. Is this a function or is this not a function? This is a relation, but is it a function? We have 3 players. They're all 6'5". Our other 2 players is 6'4". Is that okay? Sure, it's okay. There's no problem with that. It's even a common occurrence. A lot of people are the same height as other people. Okay, let's look at another example. Are these graphs functions? A graph can be a rule to tell you, when I give you an input, you give me an output. I give you the x, the domain. You give me back what is y, the range. if I tell you x is 0, where's x 0? X is 0 right here. What would you say y is? Well, it's right down there. Your y would be minus 5. If I tell you x is here, 4, what is y? Y, these are the y's, is 0. So I give you an x, you give me back a y. So looking at this rule, is this a function? Yes, it is a function, because every time I give you an x, you know exactly which y to give me. You go straight up to the graph of the function, and it tells you what is that y at that point. I give you an x, you go straight down to the graph of the function, you go over and tell me what is the y at that point. This is a function. Okay, let's look at another one. I give you an x, you give me back exactly one y. Is this graph depict a relationship that is a function? Is this a relation that is not a function, or is this a function? This is a relation. I give you an x, you get back this y, or maybe that y. You don't know. You don't know what to tell me back for any one of these x's that I give you. This is not a function. In addition to that, there's another problem. If I give you an x over here somewhere, there is no y. So this would only be, if it was a function, which it's not, it would only be a function starting here and going up to positive infinity, because it can't be a function over here, because if I give you an x, you don't know what to do. So there's two problems with this graph that make it not be a function. Let's look at another one. This one goes up, it goes down, it goes up, it goes down. Now, every point where I give you an x, you can give me back exactly one y. There's no indecision. I give you an x here, you go up to the function, you go over, you tell me what the y is. Now, if the graph is stopping right here, and if it's stopping right there, then this is a function, but it's only a function between here and here when you get an answer back. If you go outside, it's not a function anymore. So it would be a function, but only between -10 and +7. Here's another one. Is this one a function or just a relation? Well, I pick an x, the independent variable, and you give me back a y, the dependent variable. For the independent variable, I get to choose whichever x I give you. For the dependent variable, the answer that comes back, you only have one option. Give me back the y. But what happens here? I give you this x, you could either give me that y, or I give you this x and you could go down and give me that y. That's not a function. You can't have a choice of what the answer is when I ask the question. Again, if I tried to pick an x over here, there would be no answer at all. So this could not be a function over in this area, even if it wasn't already having a problem giving me two answers. Here it gives me no answers. Here it gives me too many answers. For both reasons, this is not a function. One way to present a function is as an equation. So we could write out as an equation y equals mx plus b, the equation of a straight line, where 3 is your slope and 7 is your y-intercept. A function, f of x, describes a function that gives you back your y. The function f of x gives you your y. You put in the x, the function grinds it up and gives out the y. In this case, y equals mx plus b, you put in a 2, 3 times 2 is 6, plus 7 is 13. It gives you back a 13. So when you put a 2 into your function f of x, out comes an answer, 13, which is your y. Often, you're asked to write out an equation where you have an input and an output. And the y is the same thing as the f of x. F of x is 2 ways to write the exact same idea, which is you put something in and the function will grind it up and give you something back. Here, the thing that comes out is called y. Here, the thing comes out is called the function of x, which is then equal to y. So f of x gives you back y. If you have a function, you can find y-intercepts, x-intercepts. And what the function gives you back is the y. If you draw out your function as a picture, here is your function grinding up your x's and giving you back y's. But notice that if you pick a particular x, like 4, you go up to your function, and the function tells you that y is going to be 5. So f of x, the function of x, is 5, but also, because the function of x is 5, y is 5. So giving you the answer to the function gives you your y. What I'm trying to say is that often when you're writing out functions, it doesn't really make any difference which way you write it. They both mean the exact same thing. You can write it with the letter y and say y equals mx plus b, or you could write your function f of x. The function of x is mx plus b. It's 2 ways of writing the same thing, and you may see it the same way. Either way, written out at various times on exams or worksheets. The y-intercept of this function is here, a little more than 7. And the x-intercept of this function is about 7.5. The x-intercept is the place where your function, which is the blue line, crosses your x-axis. And the y-intercept is the place where your function, which is the blue line, crosses the y-axis. The x and y-intercepts are when x is 0. When x is 0, you get your y-intercept. Here's x being 0, and there's the y-intercept. Here's y being 0 right here. And what happens? When y is 0, you're over here at your x-intercept. Okay, let's look at a function. So is this a function? Yes, this is a function. You put 1x in, you get exactly one answer back. No question what the answer will be. So it is a function. We're going to find the x and y-intercepts. So the first thing we'll do is get the x-intercept. So how do you get the x-intercept? Well, you're on the x-axis when y is 0. So we're going to plug in y is 0 and get our x-intercept. So f of x is the same thing as y. It's just another way of writing y. We can use them very interchangeably. So if f of x equals 4x plus 12 minus 12, then y equals 4x minus 12. because f of x is y. So we'll plug in 0 for y. Plug in 0 for y, it gives you back the x-intercept. So solve this out for x, move the 12 over, and divide it by 4. X is 3. So what is the x-intercept? X is 3, y is 0. Y is 0, we plugged in y is 0 to find what is x. This is the x-intercept. It's on the x-axis where y is 0. Okay, let's get the y-intercept. Same function. Y equals mx plus b. 4 is your slope. Negative 12 is your y-intercept. If you're trying to find the y-intercept, you're going to plug in x is 0, because when x is 0, that's when you're on the y-axis. So we plug in x is 0, and this is how you write it. The function of x is y equals mx plus b. The function of 0, 4 times 0 minus 12. This is doing the function to 0, doing the function to 0, and it gives you back your y, which is y equals, because f of x is y equals 4 times 0, which is 0, y is minus 12. So what's your y-intercept? X is 0, because we plugged in 0 for x, and y is minus 12. So your y-intercept is 0 for x, minus 12 for y. And we could graph the thing out very quickly. Minus 12 is your y-intercept. You're on the y-axis. And your x-intercept here on the x-axis is at 3. There's 3 on the x-axis, minus 12 on your y-axis. Graphing the function by finding the two intercepts. Okay, let's look at another function. Is this a function or is this a relation? Well, let's look at it. It's not a straight line. Y equals mx plus b. This is not. This has got something being squared. A straight line does not have anything being squared. But is it a function? Well, you take a number and you square it. 2 squared is 4. 3 squared is 9. When you square something, you only get one answer. Right? And that's what a function is. This function gives you just one answer. So if you put in any number, you square it, you only get one answer back. Subtract 12 from whatever that answer was. That's only one answer back. So yes, when you put in one number, you only get one answer back. So this is a function. Let's go find the x and y intercepts. Okay, how do you get the x-intercept? Well, you plug in y is 0. That's how you get the x-intercept. So this is your function. F of x is y is f of x. It's two ways to write the same idea. When you put in some number for x, you do the function on x, you will get back an answer, and that answer is your y. When you plug in an x, you get back a y. When you do a function on x, it gives you back an answer, which is y. So when y is 0, what is x? Well, let's move over the 12. And you're going to have to square root both sides. And now notice when you square root it, you get a plus or minus. So you get 2 x's back for a particular y. Now you may say suddenly, oh wait, maybe it wasn't a function. Wait, just because we get 2 x's go to the same y, that doesn't mean it's not a function. Remember, the x is the question. It's what you put into the function. So you could ask 2 questions and you get back the same answer. That's okay. What's not okay is if you ask 1 question and you get back 2 answers. So you put in x is square root of 12. It gives you back 1 answer. Square root of 12 minus 12. 12 square root of 12 squared is 12 minus 12. That's 0. And negative times negative is positive. So when you square negative square root of 12, it also, subtract a 12, it gives you back 0. So these both give you back an answer of 0, but that doesn't mean that it's not a function. These are just two different questions that have the same answer. Our x-intercepts places it across the x-line, square root of 12 and negative square root of 12, when y is 0. Let's find our y-intercepts. Okay, to get the y-intercept, you got to plug in x is 0. That's how you get the y-intercept. So we'll plug in x is 0, square the 0, and our y is just negative 12. So when x is 0, y is negative 12. So did this function give us two answers for the same question? No. And let's look at how let's do what they call the vertical line test. Draw a straight line up and down. Wherever you want, it only hits the function. The function is the blue line. If you draw a straight up and down line on this graph, you're only going to crash into this function in one spot. That's a way of testing to see if your relation is a function. The vertical line test. Straight up and down, it only hits at one place. Because why is that? Well, if x is any particular number, you go down and you hit y at only one spot. That means it only gives you back one y every time you put in an x. You put in x is 2, go down vertically, straight up and down, go down vertically, till you hit the y, negative 7. So it gives you one answer for every input. Everything you put in gives you exactly one answer back, and you're sure what that answer is. One common way to write out a function is with an equation. So notice that this equation is not a straight line, y equals mx plus b, because again, we have something being squared. If you have something being squared in your function is not a straight line. If f of x, the function's name is f's the x, f acts on the x, you do this to it, and it gives you back the y. And another way to think about it is just that whenever you do this, square it and add 1 to an x, that is what y is. So f of x is y. Y is f of x. It's two ways of writing the same idea. In this case, the idea is that I give you a number, I choose a number, you square it, add 1, and you have to say back the answer. Example, if our function is f of x is x squared plus 1, and we want to f a 3. So we're going to take the 3 and throw it into the function machine, and we're going to f that 3. So what happens when you do the function on the 3? Well, you square the 3, and you add 1 to it. So 3 times 3 is 9, and 1 is 10. So f of 3, when you f the 3, you get back a 10. So y is 10. Because why? Because the answer to the function, what f of x is, the answer is y. So when you do your function on 3 and you get an answer, that answer is y. That's why y and f of x are the same idea. So what happens if you throw something even more complicated into your function? Well, you can. You could throw anything you want in there. Anything that can be squared, you could throw it into the function. So let's square t minus 2. What happens when you do the function? You f the t minus 2. What happens to it? Well, you square the t minus 2, and you add 1 to it. Well, how do you square a t minus 2? Well, we've done that before. Distribution box. T minus 2 times another t minus 2. T times t, t squared, positive times positive. Positive times negative gives us a negative. Positive times negative gives us another negative. And then negative times negative gives us back a positive. So we get back t squared minus 4t's plus a 4 plus a 1. Why is the plus a 1 on the end? Because look, our function said first you square it, then you add 1 to it. So we squared it, and we got this. Then we had to add the 1 to it. F of x is y. So f of t minus 2 gives you back y. If f of t minus 2 is this stuff, then y is this stuff. Because when you do the function, it gives you back y. All functions don't have to be called f. You could name a function g if you want to name it g. So this function is g. So here you're g'ing the x. So we're going to put x into the g machine. And what does the g machine do to it? Takes it to the third power, multiplies it times 3, subtracts another x, subtracts a 2. This is what g does when you throw an x into it. So I give you some x, you g it, and you get back an answer, a y. So if you g a 2, you're going to take 2 to the third power, which is 8, multiplied by 3, subtract a 2 because x is 2, and then subtract another 2. You get back g of 2. When you g the 2, you throw the 2 into the g machine, out pops a 20. So here's your function acting on a 2, giving you back a 20. Let's have another function. We'll call this function p. We're going to p something. So what happens when you p something? You p an r. Well, if you p an r, you have to square root the r being squared and subtract 2 from it. So let's do that. We'll p a negative 3. Well, negative 3 squared, negative times negative is positive. That'd be 9, add a 7 to it. 9 and 7, 16, square root it. 4 times 4 is 16. Subtract a 2 from it, and what do you get? 2. So you p a negative 3, and out comes a 2. That's the function acting on negative 3, gives you back a 2. Is this a function? Yes. When I give you any particular number, you'll get exactly one definite answer out of it. So it is a function. It's only a relation and not a function if you don't know what the answer is. If you know specifically it is one answer and what that answer is, then it is a function. Let's go for another one. This is not a linear equation. It's not a straight line. Y equals mx plus b is a straight line. This has got a variable s on the bottom of a fraction that will not give you back a straight line. So let's throw into this function negative 2. So we'll put the negative 2 in. Every place we saw an s, we're r'ing an s. So the function is r. We're putting an s into the r function, the r machine. So in this case, we're putting a negative 2 into the r machine. And what's happening? Well, we'll take 4, right? Because it tells you, take 4 and subtract whatever the s is. So take 4, subtract, in this case, the s is a negative 2. So negative times negative is positive. So that's a positive 2. So 4 plus 2 is 6. And on the bottom, 2 plus s is 2 plus a negative 2. 2 plus negative 2 is 0. So you get a 0 on the bottom. Okay, so that's not allowed. That's where you run into a giant problem. So because you get back an answer, this is not an answer, meaning it doesn't give you back an answer for negative 2, this is not a function. For the function, you have to get an answer for every question. One specific answer, not a bunch of answers and not no answers. You need an answer for every question. In this case, negative 2 did not give you an answer. Notice that -2 is the only problem that you would run into on this function. It's the only way that you would get back an answer. The only thing that goes wrong, the only thing that will give you 0 on the bottom of the function, is if you try to put in a -2. So therefore, the domain, the things that you're allowed to throw into this function, and it would be a function, for anything except -2. So you could set your domain, set the rule for what you're allowed to throw in, to not be -2, and then it is a function. But if you try to make your domain throw in anything you want, then it's not a function, because anything you want could include -2, and that would cause you to have no answer. Because it has no answer, it's not a function at the point x is -2. S is -2. It is not a function. For any other s, it would be okay. Let's try this one. Your function is now called h. You can pick whatever name you want for a function. We're going to h an x. So we throw an x into this h machine, and out comes an answer. Well, what can't you put into this h machine? You can't put in 0, because if you put in 0, you're going to get 0 on the bottom of the function. And you can't do that, because you have 0 on the bottom of a fraction, and there's no answer. And a function always has to have an answer. So the domain for this function, h, would have to exclude, and you could not put in 0. Anything else is okay, but you can't stick in a 0. So this will be a function, yes, if the domain does not have 0 in it. And if the domain does have 0 in it, then it is not a function. If we try to put 1/4 into it, you get 2 divided by whatever goes into it, 2 divided by the 1/4. And when you're dividing fractions, a fraction, it's 2 divided by, right? So that's what a fraction is, a division. 2 divided by the 1/4, 2 being divided by 1/4. To do a division problem with fractions, you flip and multiply. So you flip the 1/4 upside down, 1/4 becomes 4/1, and you multiply straight across. So 2 times 4/1 is just 4, is 8. So when you h a 1/4, you put the 1/4 into the fraction, into the function, you get back an 8. And this function works for any x that you put in except 0. 0 is not in the domain of this function. It's not something you're allowed to put into it. Let's use our calculator to try to find the domain, the things that are allowed to put into this function f, and the range, the things that possibly could come out of this function f. Domain and range are two of our vocabulary words today. Domain, things you could throw into the f function. Range, anything possibly that could come out of the f function. So let's put this function here into our calculator. How would we do that? Well, we're going to click on the y equals button on our calculator. We're going to type in this function right here, right into the screen on our calculator. We're going to go to zoom, or the zoom button right there. Hit the zoom button. We're going to go down to zoom standard, right? Zoom standard will give us a display that we can see. Otherwise, it could be so small or so large that we can't actually see the function we just graphed. So we'll use zoom standard, hit return, and it gives us this graph. So looking at the graph, the domain is our x's, the numbers that I choose, throw it into the function machine, and then the range comes out of the function machine. So what are the possible numbers that I could throw into this function machine and it wouldn't break the function machine? And what I mean by that is, if you tried to use a number like this, x equals to 10, it will not give you back an answer. There will be no y. So you can't, this will not be a function. F is not a function if you try to make it give you answers when x is 10. You have to limit your domain. you set the domain just to those areas where there is going to be an answer. So our domain will only be from here to here, plus 6 to minus 6. We put any of those numbers in here, and we'll get back an answer. If we try to make it something bigger than 6, we won't get an answer, so it wouldn't be a function. So this is a function, but only if you limit the domain. How about the range? The range is what could possibly pop out of this function machine. So if we look at our graph here, what could possibly come out? Now the y's are what comes out of the function machine. We put the x's in, choose an x, go up to the function go over to y and tell you what is the y that goes with that x. That's what the function machine does. It goes, pick an x, go up to the function, go straight over to the y-axis, and it tells you, you read right off of it, what is the y. So what could possibly come out of this function machine? Well, notice none of these y's down here, negative y's, they never come out. Now, if you pick an x way over here at 6, you can get 0, or you could get 0 this way with a negative 6. Or if you put a 0 into the machine, you could get a 6 for y. But you couldn't get a y answer back up here at 10 or 20 or 30. The only answers, the only output, the only range that comes out of this function are things between y is 0 and y is 6. And that's our range. So we were able to look at our graph and determine the domain and the range of this function. Notice that if we don't use a restricted domain, a limit of what you can put in, then you don't have a function. So if we're calling this a function, then we have to make a limit on what you're allowed to put in and what's possible to come out. Okay, let's look again at a couple of relations, and we'll ask ourselves, how can we limit the domain in order to make these relations a function? That is, how can we choose just those things that we could put in that would be okay for it to still be a function? So let's look at one. So let's look at this relation right here. So for what domain, that is, for what values can we throw into x, for what domain will this be a function? Well, you're never allowed to have 0 on the bottom of a function, of a fraction, and so it won't be a function. So you can't have 0 on the bottom. So if you tried to make x equals to 2, 2 minus 2 would be 0, and there would be no answer. So if you tried to put 2 into this function, you wouldn't get an answer. So it wouldn't be a function. It'd just be a relation. So in order to make this a function, k is a function, for k to be a function, we need not to have 2 in the domain. So we'll need to set our domain where x can't be 2. You can't put 2 into it. So the domain doesn't include 2. So how do we write that? We need domain, and we need to pluck out the number 2. So the way we pluck out a 2 is we come right up to the 2, and then we put a parenthesis to say that it goes up to 2 but doesn't include the 2. Union on the other side of the 2. It comes right up to 2, but it doesn't include the 2. This is how we pluck out one number out of a domain. So if we make this the domain, then this is a function. If we don't make this a domain, if we try to put in any number, including 2, then this can't be a function, because a function has to give you an answer for every number you put in. And if you tried to put 2 into this function, you would get no answer, so it's not a function. But with this domain, this is a function. Let's look at another one. Is this a function? Well, let's remember, a function has to give you back an answer for any number you put in. Okay, now, if we only want real answers and not imaginary answers, we have to think about what we put under a square root. Because if you put a negative number under a square root, you get back an imaginary answer, an I. If you don't want to use I's, you only want real numbers. Real numbers are not imaginary, so you wouldn't be allowed to have negatives under a square root. So if you want this to be a function that only gives you back real answers, then you can't be putting numbers in here that's going to make this negative. So what would make this negative? We have to ask ourselves, what would cause this not to be a function if we're trying to get real answers? X minus 3 has to be either 0, because the square root of 0 is okay, that's a number, it's 0, or some positive number. And as long as you're taking the square root of a positive number, you get a real answer. So for this f to be a real function, a function that gives you back real answers, not imaginary answers, you need x minus 3 to be bigger than 0. Well, if x minus 3 is bigger than 0, then x has to be bigger than 3. Bigger or equal. So we have to set our domain. To make this a real function, we need to set our domain for x to be bigger or equal to 3. So how do we write that in interval notation? Well, bigger than or equal to 3. This is our domain. So with this domain, x bigger than or equal to 3, this becomes a function. And for k is a function if you use the domain negative infinity to 2 union 2 to infinity, not including the 2. This is a function. Okay, let's look at another relation. We'll try to figure out how can we restrict the domain in order to make this relation into a function. So here's our relation. Now notice this is not a straight line, y equals mx plus b. This has squareds in it, and it has variables, x's, on the bottom of a fraction. So it will not be a straight line. It's curvy. So let's think about why this would not be a function. Well, it will not be a function if it doesn't give you an answer for every x you put in. Because we have variables on the bottom of a fraction, we know right away what we need to look out for is how would we end up with a 0 on the bottom of a fraction, which we're not allowed to do that. So let's find out what x's would not be allowed for this relation. So let's factor this thing apart. Numbers that you multiply together to get to -6 and add to get to -1. 2 times 3 is 6. Because it's -6, one's positive, one's negative. Positive 2 plus -3 will give you a -1. Positive 2 times -3 gives you a -6. So there's your winner. So this polynomial quadratic equation here factors into these two factors. So now we can see very clearly what's going to give us a 0 on the bottom, right? 0 product property. If either one of these is 0, then there's going to be a 0 on the bottom. So x can't be a -2, and x can't be a +3. Those are the two things x can't be. Now, any other x you stick in there, you're going to get an answer. So this is going to be fine. It will be a function. But it will not be a function if there's some number that you stick in here and you can't get an answer. And for those two, -2 and +3, you won't get an answer, so it won't be a function. So we can make this relation into a function if we restrict the domain. So we'll restrict it by plucking out the -2 and the +3. So how do you write that in interval notation? Well, you pluck it out with bringing the interval all the way up to the -2, and then stopping just before the -2 with the parentheses. Union, rounded parentheses, and -2, go all the way up to the 3, then stop again, rounded parentheses, union, On the other side of the 3, rounded parentheses, we've plucked out the -2 and the 3, and with this domain, this is now a function. If you tried to make this a function on the entire any x's, negative infinity to infinity, it won't work because there's 2 places you won't get an answer. Okay, let's try this again. Same idea. Let's take this relation and let's think about how can we restrict the domain so that this relation will be a function. So for what values that you could put in here, put in for x, what x values can you put into this function machine? The function machine is h. What values can you put into h that will not give you back an answer? Because you can't do that and it won't be a function. So we have to figure out how can we restrict the x's to go in, and then it will be a function. So for what x's will this thing not give you an answer? Well, we have 2 different problems going on here. Problem number 1 is you can't have 0 on the bottom of a fraction. So whatever would make this bottom here 0, that's not going to work out. Problem number 2, if we're trying to get a real function, a function that gives you back real answers and not imaginary answers, no i's, then we can't have a negative number inside the square root. So we have 2 different problems, issues, restrictions on this function. One restriction, this can't be 0. And the other restriction is this can't be negative. So let's think about how we would write that restriction out and test it. Can't be 0 and it can't be negative. So this stuff here has got to be something, not negative, bigger than 0, right? It's not negative, it's bigger than 0. And it can't be equal to 0. So this, the bottom of the fraction here, inside the square root, has to be a positive number. That's the negative number will not work, and a 0 will not work. So we have to set this bigger than 0. So we get back a fraction answer. X has to be bigger than 5/2. If we make x bigger than 5/2, then this will be a function. But we're going to have to restrict our domain, so the domain is only x's go in there. The domain is the x's that you put into the function. The only x's that go into this function have to be bigger than 5/2. So how do you write that interval notation? Interval notation, not including the 5/2, rounded parentheses, not including the 5/2 all the way up to infinity. If we make our domain this, then h is a function. If we try to include other things into the domain, then h would not be a function. H is only a function if it gives you back an answer. And without the restricted domain, there'll be numbers going in that will not have an answer, and it won't be a function. Okay, let's look at a picture here of this graph, and we'll try to answer some questions. Now, let's notice first off that our blue line here will be a function as long as we stay within a domain for which there's an answer for every x. Right? So notice over at 5, when x is 5, you don't get back any answer. There's no y value, because when you go up and down when x is 5, you don't ever come to the function. So it can't tell you how to get over to a y. At 2, you go down to the function when x is 2. It takes you over to -2, and you know y is -2. So that function gives you an answer. The function gives you an answer for any number of x that you put in, as long as you stay down here below the 4. So let's look at the questions. F of -2. So notice on our graph here, we're using f of x for the name of the y-axis. And it's okay. F of x is y. Y is f of x. It's the same idea. You do something to an x and you get back a y. This function here gives us back a y for every x. We could call our x-axis f of x, because f of x is the answer to the function. Let's find f of -2. So when f is -2, we put -2 in for x, Go up to the function, and you get y is 1. That's why y is 1 when x is -2. The function, our graph, the function, tells us what the answer is when f is -2. Okay, how about f is 4? What is our answer when f is 4? So we put 4 into the function. We go over to x is 4. We come down to our function, and we find a hole, meaning there is no answer. So our function is not a function at 4. If we ask the question of 4, we get no answer, then that means that we have to exclude 4 from the domain. The domain has to start after 4 and go all the way to negative infinity. It can't include 4. It can't include 5 or 6 or 7 because none of those x's will give us back an answer for y. The only places we get our answers for y is if we can go straight up or down to the function, the line, and it goes over and tells us the y. So f of 4 has no answer. So our domain has to start on the inside of the 4. Okay, so now find all the x's. Next question. Find all the x's for which f of x is 3. Okay, well, where is f of x 3? Well, y is f of x. F of x is y. So where is f of x? This is our y. Y is 3. Y is f of x. So when is, for what x, is our y a 3? Well, let's come down here to 3, and go over to the function. There. So what x did we have to put in order to get 3 for an answer? -4. We put -4 in, come up to the function, go over to 3. So f of -4 gives us back a 3. So for what x's will f of x be 3? F of -4. That's the only x for which f of x is 3. Okay, what about the next question? All the x's for which f of x is 1. Okay, so we need to find out where is f of x 1. Here's f of x. Here's f of x being 1 right here. Y is f of x, coming down the y-axis to 1. So for what x's would you put in to get back a y of 1? Well, let's look. If we put in x is 2, -2, and we came over, then y would be 1. If we put in x is -1, here's the x's, x is -1, put in -1, come up to our function, that will give us back 1. If we put in x is equal to -3, put it in, go up to our function, x gives us back, f of x gives us back a 1 for an answer. So for any one of these numbers here, and anything in between, if we put those into the function, we're going to get back an answer of 1. So for all the x's between -3 and -1, our y answer, the f of x answer, the answer out of the function will be 1. Okay, next question. What is the x-intercept of this function? The x-intercept of this function is the place that it crosses the x-axis. So where does our function cross the x-axis? Well, here's the x-axis, and our function, the blue line, crosses the x-axis right here at the origin, 0, 0. So when x is 0 and y is 0, that's when we're crossing the x-axis. So our x-intercept is 0, 0. Next question, the y-intercept. Here's the y line. When does our function, the blue line is our function, when does our function cross the y-axis? That'll be our y-intercept. Here's the y-axis. So when are we crossing the y-axis? Well, right here at the origin. And the coordinates at the origin are 0, 0. So our y-intercept, 0, 0. Next question. What is the domain of f of x? Well, we talked about this, that you can't choose x's. X's are in the domain. The things you put in to the function are the domain. You can't choose x's over here bigger than 4. You can't. And you can't even choose 4. So we need to set our domain. If this is going to be a function, if f is going to be a function, we need to set our domain to be everything less than 4. So we'll use our rounded parentheses to show that 4 is not included in the domain. The domain starts at 4 and goes down to negative infinity, but it doesn't include the 4. Okay, so now about the range. The range of a function is what could possibly come out of the function. So here's our function here. What could possibly come out? Well, notice that the function starts here and goes up. It never comes down any lower, right? So no place does a function ever get, the y values that come out of the function, that's the range, the things that come out of the function, never did they get down here below -4. It's always -4 and above. So the range of the function, the stuff that could possibly come out, has to start here, right? You put an x in, and you get a y out. Well, the things that can come out are bigger than -4, because no matter which x's you put in, and you're not allowed to put any of these x's over here in because they're out of the domain. But for the x's that are in the domain, whichever one you put in, the y's keep getting bigger and bigger and bigger. They never get to be less than -4. So our range has to start at -4 and go all the way to negative infinity.